Hey guys, today we're looking at section 5.5, zeros of polynomials. So zeros of polynomials, basically what are we going to be using this for? It's to help us graph these things. We're going to be using these when we're trying to find x-intercepts. So when we have a polynomial f of x is equal to x cubed plus x squared plus 1, finding a zero of a polynomial is basically saying what number do we plug into f, right? What's the number that's going to go in here? That's going to make all of this right side equal to 0. If we can find that, then x is some number, y is 0. That tells us that it's an x-intercept. And so that will help us graph polynomials. The problem is, up to now, we've really only had techniques to figure out zeros for things that are quadratic or less in power, right? So if we had an x cubed and it wasn't a perfect cube like this, we don't know how to factor it. This one we do because we have a technique for it. But if I even add just one number, it becomes unfactorable for us. So this technique that we'll learn in this section will help us find some x-intercepts for these polynomials. Now, one thing that we want to understand is the factor theorem before we get into all that. And the factor theorem tells us that if x minus a is a factor of f of x, then f of a is equal to 0. And so an example to illustrate that is if f of x is x squared minus 10x plus 25, well, if we were using the AC method, we would say what multiplies to 1 times 25, which is 25, and adds to negative 10. Well, those numbers would be negative 5 and negative 5. And since this is a 1, we can just write x minus 5, x minus 5. And so if we did long division from our last section, x minus 5 into x squared minus 10x plus 25, you'd find the answer to be x minus 5. And so x minus 5 goes into x squared minus 10x plus 25, x minus 5 times. So the quotient is x minus 5, which tells us that if we plug in 5, x equals to 5, we should get 0. So maybe this is something that you already understand, but it's something that we need to talk about explicitly. And so if we plug in 5 into our function f of x, which is 1x squared minus 10x plus 25, we replace the x squared with the 5, the x with the 10x with the 5, and 25, and now we just calculate. 5 squared is 25, negative 10 times 5 is negative 50, and plus 25, and 25 here make positive 50, minus 50, and we get our 0. So that's an illustration of what if x minus a is a factor of f of x, then f of a is equal to 0. All right. So the next theorem we're going to look at is the important one for the section. And this is what's going to give us a technique to find zeros for polynomials that we do not know how to solve for, i.e. they're not quadratic or linear. So if a polynomial has integer coefficients, integer meaning whole numbers, positive or negative, the list of possible zeros is p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. And so remember, the leading coefficient is the number that's associated with the largest power of x, the number that's in front of the largest power of x. So in this abstract example, an would be the leading coefficient, and our constant term would be a0, the term basically the one that doesn't have any x's in front of it. And so this is p, and this is q. And all of our factors are going to be in the form of p over q. Factors of p, factors of q. So let's go ahead and try to use this rational zeros theorem and see if we can come up with any x's for our problem. So here is f of x. We have f of x is equal to 2x cubed plus 7x squared plus 7x plus 2. And so we may want to see what are the possible zeros, because if we can find the rational possible zeros, we can kind of just plug them into f of x and see if we get 0. Okay, so to figure out what the list of possible rational zeros is, the theorem before told us it's all the factors of p over all the factors of q. And so this is p, this is q, and it's just the 2, just to be clear. It's not the x, it's just the 2. What are all the factors of p, both positive and negative? Well, you have 1, of course, because it's always a factor, so you have plus and minus 1, and then you have plus and minus 2. And since q is also 2, well, you have plus and minus 1, plus and minus 2. And so our possible zeros, p over q, come out to be plus or minus 1, plus or minus 2, over plus or minus 1, plus or minus 2. And basically you take every combination of this that you can. So for instance, we would have positive 1 over positive 1, which is just 1. So 1 is going to be added to our list. So list of possible rational zeros. So 1 is going to be here. Well, we can also do negative 1 over 1. That's going to give us negative 1. So negative 1. If we do plus 1, if we do negative 1 over negative 1, well, we're just going to get 1 again, and that's a repeated one, so we don't need to add it. And so what you'll notice is, because 1 is always going to be a factor, you're always going to get these numbers on top, and they're positive and negative versions. So we're going to get 1, 2, and then negative 2. And then, not only that, we've already used all of these guys. You're going to get the fractions. So 2 over 2, this is just going to give us 1, so we don't even need to worry about this. And so our last two rational zeros are going to be 1/2, or our last two possible rational zeros are going to be 1/2 and negative 1/2. And so from here, you can either use synthetic division to check whether these are regular zeros, or just plug these in. And so to do that, I'm going to plug in 1 first. So if I say f of 1, so I'm just going to write f of x up here, 2x cubed plus 7x squared plus 7x plus 2. And f of 1 is just going to be, replace all the x's with 1's. So 2 times 1 cubed plus 7 times 1 squared plus 7 times 1 plus 2. 1 cubed is going to be 1. 2 times 1 cubed is plus 7 times 1 squared plus 7 times 1 plus 2. This is going to give us 2 plus 7 plus 7 plus 2. And so is this going to add to 0? Definitely not, because these are all positive numbers. So this is equal to 18, which is definitely not 0. And recall the first theorem we covered, the factor theorem. It's only a factor if f of a is 0. So we're using this to find factors of our polynomial. And so 1 definitely doesn't work, but let's go ahead and try another number. And so why don't we try f of negative 1? So if we do f of negative 1, it's 2 times negative 1 cubed plus 7 negative 1 squared plus 7 times negative 1 plus 2. And so this is going to give us 2 times negative 1 cubed, which is just negative 1, plus 7 times negative 1 squared, which is just positive 1, plus 7 times negative 1, and then plus 2. So this is going to give us negative 2 plus 7 minus 7 plus 2. Okay, and it looks like here we're actually going to get 0. Negative 2 and positive 2, these two combine to make 0. And 7 and negative 7 combine to make 0, so we get 0. So we found one. So if f of negative 1 is equal to 0, using the factor theorem, that tells us that x equal to negative 1 is going to make f of x 0, right? X equal to negative 1 makes f of x equal to 0, which tells us that x plus 1 is a factor of f of x. And so when we say x plus 1 is a factor of f of x, that means if we do long division or synthetic division of f of x by x plus 1, we're not going to end up with a remainder. Okay? So if we imagine for a second that we were given this polynomial and we were told to find what are the x-intercepts, well, you would use the rational zeros theorem because this isn't something we know how to factor necessarily. And so you would use the rational zeros theorem to see if you can find numbers that actually do make this zero. Once you find one, like we did with the -1, what you're going to do is take, since we know -1 is a zero, that tells us x plus 1 is a factor. And so now you can do synthetic division with the -1 into our polynomial. And so our polynomial was 2x cubed, so I'm going to write the 2, 7x squared, 7x, and 2. And we covered synthetic division in the last section. The first term just comes down. 2 times -1 is -2. We add 7 to it, we get -5. -1 times -5 is +5. Oh, I made a mistake. Sorry about that. Not this one. -7 plus 2 is +5. And then -1 times 5 is -5. 7 plus -5 is 2. 2 times -1 is -2. We add these two together, we get 0. And so that tells us our polynomial that we're going to be left with is 2, because we had x cubed, it's going to be 2x squared plus 5x plus 2. And so essentially what we know is that this now times the x plus 1 that we started with is equal to our original polynomial, right? And that's why it was able to divide in evenly, because if this wasn't true, we wouldn't have this 0 remainder that we ended up with here. And so, okay, we have one of the x-intercept, right? We know -1 is a 0. And now, because we've reduced our trinomial into a quadratic, we can figure out what the zeros of this are. And so you can use any method that we've learned up to this point. You can use factoring by hand. You can use the quadratic formula. You can use completing the square. Whatever you'd like to solve this one. And so if you were trying to solve by hand, well, you would need a number that multiplies to 4, right? 2 times 2 and adds to 5. Well, the only numbers that multiply to 4 and add to 5 is 2 and 2 and 4 and 1. And so it looks like 4 and 1 work, right? So we'll take this guy here. We say 2x squared plus 4x plus x plus 2. And now we can factor by grouping because we have 4 terms. What is the greatest common factor of 2x squared and 4x? Well, 2x. What's left on the inside? X plus 2. And what can we factor out of x plus 2 with the greatest common factor? Well, it's just 1. And so what's left on the inside is x plus 2. We have a match, so we have x plus 2. That's one of our terms. What's left on the inside is our other term. And so now 2x squared plus 5x plus 2 can be written as, originally we had 2x cubed plus 7x squared plus 7x plus 2. And then we said that we could break it down to 2x squared plus 5x plus 2 times x plus 1. And now we've broken this one down even further, so we have x plus 2 times 2x plus 1 times x plus 1. And now we can set either of these, all of these set equal to 0 if we were finding x-intercepts, for instance. And we would solve for 0 for each of these. So x plus 2 equals 0, 2x plus 1 equals 0, and x plus 1 equals 0. And that would tell us x is equal to -1, x is equal to -1/2, and x is equal to -2. And so our x-intercepts for this function would be -2, 0, -1/2, 0, and -1, 0. Okay, so this technique is going to be a tool. This rational zeros theorem is going to be a tool to help us find zeros of polynomials that we don't have techniques to solve yet. Now we do. And we're going to be using this technique to find x-intercepts of polynomials so that we can graph them. Because up to this point, we wouldn't have been able to figure out what the x-intercepts of this polynomial were. We would only be able to do it if it was already given to us in this form. And since we weren't capable of that, the problems we were doing in the previous sections to graph polynomials were only written in this form. But now, if the polynomial is written in this form, we're going to be expected to figure out how to graph it by finding the zeros ourselves using the rational zeros theorem. So that's going to end it for this video. If you guys have any questions, go ahead and let me know. I'll see you next time.